Okay, this section is the first law of thermodynamics, and the goals are to recognize how energy transferred as heat and work done on or by a system contributes to the internal energy of a system. Calculate the work done by system by the expansion of gas against a constant pressure. Calculate changes in enthalpy and internal energy, and recognize state functions whose values are determined only by the state of the system and not by the pathway in which the state was achieved. Our focus really is on this last one, although we do talk about these other things here. I don't really have you do calculations based on pressure and volume because we really haven't covered gases yet. Okay, so first law of thermodynamics basically says that let me change this, that the internal energy of a system is equal to the sum of the heat of the system plus the work of the system. And this becomes the change in internal energy is equal to Q plus the change in work. Now, Q stands for the heat energy and W stands for work. And there is some sign convention. So here we already understand that endothermic means that Q is greater than 0, which is another way of saying it's positive. Exothermic means energy is released by the system. So Q is less than 0 because it's negative. Now, if you have work on a system, then work is considered to be greater than 0 and that energy is absorbed by the system. If you have work done by the system, then W is less than 0, it's negative, and energy leaves the system. So in each case, this is the effect on the internal energy. For an endothermic process, the internal energy increases because energy is absorbed. But also if work is done on the system, the internal energy increases because that energy is absorbed. On the other hand, if energy is released in the form of heat, the internal energy of the system goes down. And if the system does work on something, it loses internal energy and it goes down. Now, let's see how work affects all of this. So work is a product of pressure times the change in volume. So work, and this is at constant pressure, and P is pressure, and change in V is the change in volume. Now here, if we take a look at this, we see that if the change in V is positive, then this value ends up being negative, and that is the system doing work, so losing internal energy. However, if the change in volume is negative, then work is done on the system, and the system absorbs that energy, an increase in internal energy. What I've done here is I've drawn for you a photograph that they have in the book, but this is my cartoonish drawing of it. And this shows you a sealed bag with dry ice in it, which is a solid, and a book on top of that bag. Now, if that bag is sealed, the dry ice will turn into CO2 gas. And when it turns into gas, the bag inflates. And when the bag inflates, the book will rise. So you can see that the system here, if it's the CO2 in the bag, is doing work on the book because it's raising it. So if it's doing work on the book, the system does work. You are losing energy from your system. And here you can see that the change in volume is positive, so you're losing energy. Let's take a look at one calculation here. I haven't tried this in a while, but we'll give it a try. Nitrogen gas is confined in a cylinder under constant atmospheric pressure, and that's 1.01 times 10 to the minus or 10 to the 5 pascals. The gas expands to a volume of 2.18 liters when 882 joules of energy is transferred as heat from the surroundings to the gas. What is the change in the internal energy of the gas? Okay, so we're basically going to do this calculation where we're going to do a work calculation. Work is equal to negative P delta V. So here, the pressure is 1.01 times 10 to the 5 pascals. Now we have to understand that a pascal is a kilogram meter per second squared. So, and this is times a change in volume, and the change in volume expands to 2.18 from 1. So 1.8 liters minus 1.50 liters. So we're going to change this to, and there should be a negative here. So this becomes negative 1.01 times 10 to the 5th pascals. Well, I don't want to use pascals. I'm going to put kilogram meter per second squared. Okay. And here the difference is what? 0.68 liters. Let's make sure I did that right. 2.18 minus 1.50, 0.68 liters. Now, we're also given this value over here that a meter cubed is 1,000 liters. So we can multiply by 1 meter cubed per 1,000 liters. So when we do all of this, we get, we'll do all the work. We're going to get 1.01 second EE 5 times 0.68 divided by 1,000. And we'll end up getting negative 68.7. And actually, we need to round to just 2 zig figs. Negative 69. And we'll get a kilogram here. And you can see we have meter cubed on top and meter on the bottom. So we'll end up with meter squared on top. And then the liters cancel and we'll have seconds squared. Now, it turns out that this is the definition of a joule, a kilogram meter squared per second squared. A lot of physics here. So the work is negative 69.8, and it's a negative value, which means that the system does work. The gas expands. So when it expands, positive change in volume, it does work. So here's the change in your internal energy. Now, I should actually say that we also need to calculate this. So we're not quite done. We have 882 joules transferred as heat from the surroundings to the gas. So this is going to be a positive because it's absorbed. And then we have the minus 69 joules. So when we put it all together, let's see what we get. 882 minus 69, and we get 813 joules. So there's your change in internal energy. You're not going to see a problem like this on the test. Okay, the other things I want to talk to you about in this particular section is this idea of enthalpy. Enthalpy has the symbol H, and we're really not interested in H so much as we are interested in change in enthalpy. So your book goes through this whole derivation where the change in internal energy is Q plus W. Therefore, the change in internal energy is Q at constant pressure plus W. And here, since W is negative P delta V, we have change in internal energy is the heat plus P times change in volume. And here, you can see that things have been switched around a little bit. Enthalpy H, H is equal to U plus PW. And so when you put it all together, you get that basically change in enthalpy is the heat of the system. All right. So you're not going to have to derive any of this. What is your take home from this? Your take home is we have a new term. It's called enthalpy. Enthalpy has the symbol H. And we're not really interested in enthalpy. We're interested in the change in enthalpy. And the change in enthalpy is basically the amount of heat that is absorbed or released by a chemical reaction. or process. Okay, and the last little thing about this section is something called a state function. A state function is a function whose difference depends only on the initial and final state, like a change in altitude. If you go from Eureka to Denver, your change in altitude is about 1 mile, because Denver is the mile-high city, whereas we are the zero-high city. Okay, and that's probably why Colorado made pot legal first, mile-high city. All right, so in this case, the change in altitude is a mile high. It doesn't matter whether you drive from here straight to Denver, or if you go over the Rocky Mountains, which is around 14,000 feet, then drop down into Denver, your change in altitude is 5,000 feet. In fact, you could get on an airplane, fly at 40,000 feet, drop down into Denver and be at 5,000 feet, and your change in altitude is still only 1 mile. So your change in altitude, the pathway doesn't matter. Now, it turns out that the change in internal energy and the change in enthalpy, the pathway doesn't matter. These are also state functions. Now, it does make sense to try and think about something that is not a state function. And an example of something that is not a state function would be the distance traveled from Eureka to Denver. So if you went straight from here to Denver via plane, it's about 1,000 miles as the crow flies. If you drive there, about the shortest distance you can go is about 1,500 miles. So the distance traveled from Eureka to Denver depends on the pathway. Are you going to drive there on a straight route? Are you going to fly there on a straight route? Or are you going to go a roundabout way and go visit Yellowstone first, then go across Idaho and maybe drop into Colorado and see Denver? Who knows? Maybe you want to go to LA first and come up from the south. So the distance traveled depends on the pathway. Now in chemistry, for us, we're going to find out that this delta H, that it doesn't depend on the pathway, is going to be very useful for us to understand energy changes in chemical reactions. And that is the shortest section of this book, or of this section, I should say, this module. All right, thank you.